Hi everyone, my name is Kira Duwe and I'm from the Otto-von-Guericke University in Magdeburg. I will present the research Michael Kuhn and I did on dissecting self-describing data formats to enable advanced querying of file metadata. So, as you all know, scientific research has become increasingly data intensive. Performing meaningful analysis is getting more and more complex, and for most approaches, efficient data sifting is essential. However, the hardware and software architecture of HPC systems complicate this task, and a typical I/O stack looks similar to the one on the left. This separation between the individual layers allows exchanging them relatively easy, but the layers are often optimized for different goals, which can lead to performance and management issues. I/O libraries, such as NetCDF and ADIOS2, are used to make data handling easier for the application developers and users. Unfortunately, the associated file formats are unaware of the I/O stack, which limits the potential performance, and furthermore, these libraries and most parallel file systems are built on outdated assumptions and mostly rely on the POSIX-AO interface. And to make this stack simpler in our project work, we replaced Lustre with the JULEA storage framework. You can see the I/O stack on the right. And JULEA provides flexible storage building blocks like clients and backends for key value stores and databases and object stores. And I will explain it in more detail later. So, the mentioned I/O libraries provide so-called self-describing data formats, or short SDDF, like ADIOS2, NetCDF, and BP3 and BP4. And besides easing the data sifting, the goal is to provide self-explanatory data that can be exchanged between researchers easily without requiring prior knowledge to access the data. And this is accomplished by the options to annotate the data with additional information, for example, about the experiment. And all of these formats support the notion of variables and attributes. And while ADIOS2 focuses on hierarchical structuring, ADIOS2 aims for a very flat namespace. And though differing in the exact metadata associated with a variable, the variable concepts can be mapped onto or transformed into one another. And we think there is a problem in how this type of metadata is treated. So the distinction between file content and file system metadata, such as timestamps, is long established. However, we propose to split the file content further into file metadata and file data. And file metadata is the core feature of an SDDF. It is the structural information about the data as well as annotations and additional statistical metadata like minima, for example. And currently the file metadata is stored within the file on data servers, and there it is treated as data and can therefore only be accessed using optimizations for data retrieval, such as large continuous reads. However, metadata accesses are typically small and random. And to show how this is relevant, we look at climate research. There, a simulation output can reach several petabytes for large ensemble runs. And this data needs to be stored for decades to validate the models. So for cost and maintenance reasons, the data is archived in tape storage. And let's take a look at the following example of an ADIOS2 variable. The variable has several time steps with one block per MPI process. And ADIOS2 automatically determines and stores the minima and maxima of every block, of every step for all variables. And if you want to locate all blocks within a specific value range, all files have to be read because the file metadata is stored inside the file itself. And in the worst case, this means reading the data from tape, which introduces large latencies of minutes, even up to hours. And so by storing the file metadata separately, only accesses to the variables meeting the query expression are required, instead of scanning the complete data. And this is where we see great untapped potential. And therefore, we dissect the file format and store the file metadata in a database and the data in an object store. This means that we do not duplicate data. We do not store the file metadata in the database along with the file, but instead. And to give more details how we realized our approach, a bit more information about JULEA is required. So JULEA is a storage framework which offers high flexibility. It is a user-space system which is very useful for the development and debugging, but also the deployment on large HPC clusters, as no root access is necessary to run it. And JULEA supports a multitude of technologies, among others SQLite, MariaDB, MongoDB, LevelDB, LMDB, and the general JULEA architecture is shown in the figure on the right. So when using JULEA, the application interacts with one or several JULEA clients, and the clients communicate with the backends. And the backends are managed by server processes on the appropriate nodes. And the backend interfaces are very generic, so that the actual implementations can be easily exchanged. So it is possible, just by adapting the configuration, to switch the database backend, for example, from SQLite to MariaDB. So now both metadata types are handled by metadata servers. On the right, you can see the separation of the SCDF file, which is handled by an ADIOS2 engine. And the engine concept is similar to the vol plugins in HDF5. Using this engine, there are no application changes, which is crucial to get users to even try it out. And the fine-grained patterns show the file metadata that is now handled using databases. Again, we do not store the BP file anywhere to avoid duplication. We store the data in object stores and the metadata in databases. However, we can still export the original file format. And as we do not store the file, we are not limited by the format to what metadata we can store. So the separation allows us to compute and store new information that would otherwise require format changes. For example, we extended the statistical data that is captured for every ADIOS2 variable to also contain the mean value. And furthermore, we provide a new interface called the Data Analysis Interface, short DAI, and it allows us to access the file metadata directly and makes querying it easier, even across multiple files. For example, finding all datasets with the mean temperature for the last 12 months has been higher than 10 degrees Celsius, for example. So, next I explain our setup briefly, and then I will present the results of our evaluation of the different engines. So we examined both the write and read performance of a typical application and of file metadata queries. We used 4 compute nodes. Each is equipped with 4 AMD Opterons, 128 GB of main memory, and 1 TB Western Digital HDD with a writing performance of roughly 110 megabytes per second. Our Lustre has 10 nodes with 2 TB HDDs each and a 160 GB SSD for the metadata. And the compute nodes are connected to Lustre via gigabit Ethernet. And JULEA writes to the local compute node local storage, and BP3 and BP4 write to Lustre. So, to evaluate the read and write performance, we used the heat transfer application from the ADIOS2 repository, and it solves the 2D Poisson equation for the temperature distribution in homogeneous media. And the data rates are shown in this plot, and they are the mean values of the individual I/O times of each process per step over all steps. And to get the rough estimate of the performance difference between the node local storage and Lustre, we used BP3 and BP4 to write to one compute node and also to Lustre. And Lustre achieved at maximum double the performance of the local storage. So, using our setup, we cannot directly compare the performance of the engines. However, taking the hardware differences into account, we see that our engine is competitive to the native ADIOS2 engines. And the main focus of the evaluation was to demonstrate the value of the format dissection it has for query and post-processing. And for this, we developed two applications, ADIOS Query and JULEA Query. And the question we want to answer in our example is, what block does have the largest difference between its mean value in step 1 and step 5? And ADIOS2 Query uses the ADIOS2 API to query the data. And to answer the question, it needs to read the complete data of step 1 and step 5 and compute the mean value for each block. And it then needs to determine the index of the block with the largest difference between its two mean values. And we evaluated both the native BP engines and our engine this way. But to validate the usefulness of the separation and therefore the DI interface, we also wrote a query application directly interfacing the JULEA storage system. And using the JULEA API, we can access the mean value that has been pre-computed by the JULEA DB engine when writing the data blocks. And this query application therefore does not need to access the object store containing the data, and it is sufficient to read the mean values from the respective databases and compute the differences accordingly to the ADIOS2 query. And as the plot clearly shows, JULEA Query is incredibly fast and does at maximum not even take 1 second to finish in comparison to ADIOS2 Query, which takes over 600 seconds. However, we do want to highlight that the important aspect is that we can reduce the data access. The improvement factor itself is not very meaningful. It depends largely on the data size and the read performance of the hardware. So, in summary, we were able to show the possible performance improvement for data querying that can be achieved by separating the SYSTOR into file metadata and file data, and by storing the file metadata in the appropriate backends in JULEA, we also gain the flexibility to introduce new metadata that can be pre-computed, and this will help reduce data accesses. And one of the key aspects we will focus on in the future is to extend the data analysis interface so that users can specify values or custom operations that should be calculated and stored in the database for faster post-processing. And we will also work on supporting external tools such as the climate data operators. And furthermore, we will use structural information in the form of file metadata for intelligent hierarchical storage management in tiered storage systems. So, we want to thank the DFG for funding the Cosmos project, and thank you for listening.
Thank you, Kira, for the extensive work and the great presentation. Yeah, we have a question on Slack from Joe. So Joe, could you unmute yourself and ask the question by yourself?
Sure. Hi, I really like these kinds of projects. I think it's a great way to advance the way that we deal with our data. The problem is that how do you integrate it into an existing system can sometimes be very challenging. Like, for example, accessing metadata can be done with stat or some other well-known system calls, but they're quite limited. It sounds like you want to provide a very extensive query language. So do you have any insights into how you can do that in a standardized way?
Yeah, so first of all, we tried to separate the metadata, which is already present in the file format. So the first step was to really just take the information already provided with the format and store it in a more accessible way. And what we want to do next is, because we also see the interface challenge, as that for one, we want to implement some climate data operators so that the additional metadata can be accessed using typical climate simulation post-processing tools, so that we do not have to use or provide typical file system metadata methods, but a more file metadata focused approach. I'm not sure whether that answers the question.
Yeah, I think so. So you're talking about using specific database query languages rather than trying to integrate it into a generic file system.
Yes, that's right.
Okay, thanks.
Thank you for the question. Yeah, just a quick follow-up. So I'm wondering if there would be any reliability concerns if we skip, the file system. So conventionally, people have relied on file system for various, security and data management features. So without it, so how can we deal with it?
Yeah, so this is obviously not a production-ready file system replacement. JULEA is really more intended as a playground to see whether new approaches would be sensible, and to have an option to easily check whether a new idea is sensible or not. Because if you have to integrate it into Lustre, for example, that takes a really long time. So we are really only starting, because currently I won't recommend storing the data using JULEA and rely your very trusted data to it. So yeah, we are just starting there.
I see. Yeah, makes sense. It's really impressive to me that this work supports so many different storage backends, and you worked really hard to make it open source. So I'm wondering how much effort is required, say, if I want to extend the framework to to work with another storage backend.
That largely depends on whether we can use a prototype we already have, because if you want just another SQL database, it's really simple to add that. If we want to add NoSQL databases, this is a bit more work, but the interfaces are very generic, and it's doable by a bachelor student. So we have several that are working on extending the current backends.
Okay, great. Thank you so much, Kira, for the talk.